Hello everyone. This video is going to feature the restoration of an original 9-inch South Bend Lathe electric motor and also the drum switch that operates it. This particular motor and the lathe was from 1934. This appears to be the original motor on the lathe. Most of the 9-inch lathes at that time were supplied with 1/4 horsepower General Electric motors, and that's what this is. This particular type of motor is referred to as a split phase design. It's a very simple design, and there's a little centrifugal switch in there, and as long as that switch is kept clean, there's not very many things to go wrong with it. So the way that you switch direction on a split phase motor is you just flip-flop the leads on one of the windings. I have a little diagram which I'm going to show you here in a second of how they work. But just flip-flopping the leads on one of the sets of windings will change the direction of the motor. So that's all that drum switch does. It just flip-flops the leads. Anyways, this particular motor is rated for 115 volts, and at that time they were transitioning from 110 to 115, and then of course we eventually transitioned to 120. So we're going to go ahead, we'll take a quick look at the diagram, and then we're going to start tearing this motor apart. So here's a little chicken scratch drawing showing the basic layout of a split phase motor. You look at the drawing, you'll see that there's two sets of windings. One is labeled the run winding, the other one is labeled the start winding. Then you see that S with the two lines, that stands for switch. So as its name would imply, the start winding is only in action when the motor is starting. After that, the switch, where the S is, opens up and the start winding is disconnected. So when the motor is stopped and the motor is at a standstill, that switch is closed, it's connected. And then as the motor starts, centrifugal force causes the flyweights in the switch to open up, and at that point that switch disconnects and the start winding is removed from the circuit and the motor is just running on the run windings. As I was explaining earlier, to switch direction on a split phase motor, all you have to do is switch the leads on one of the sets of windings. So when you're looking at that drum switch, that's all it's doing. It's just flip-flopping the leads, and that's how you switch direction on it. So it's a pretty simple design. Anyways, we're going to start tearing this motor apart. Here you can see the original cloth-covered wiring on that. Some of that insulation is missing, but that gives you an indication of the age of the motor. And then over the years, I took the cover off here. You can see that somebody switched this cord out, but it's still pretty old. You see how yellow those wires are? So it's a newer cord, but it's still been in there for a long time. So here's the leads coming out into the switch. I took the cover off the drum switch, and you can see those yellowish looking cords are your 4 leads coming out of the motor. And then these two here are the ones that are connected to your power cord, and this green one is a ground wire. So as luck would have it, when I took the cover off that drum switch, there was still an original wiring diagram inside there, right? On some kind of fibrous material. It's probably asbestos. I'll be sure not to eat it. Anyways, if you look here, this shows the wiring for different types of motors, okay? And in the upper right-hand corner here, this is the wiring diagram for a split phase motor. And you can see the two sets of windings there, so that represents 4 leads. Obviously those are the ones coming out of the motor. And if you look at the diagram, you can see that 3 of the 4 leads are connected on one side of the drum switch, and that the other lead is connected to the center contact on the drum switch, and then these 2 leads are for your power. So that's nice to have that in there. That was a nice little surprise. When we finish putting the motor back together, we'll put that back in there. So anytime I take anything apart, I make it a habit to label things whenever possible. So since this was already hooked up, I just labeled it, and it'll make it easier when we put it back together. So I took the 3 leads off of this side of the drum switch, and this one I labeled ACH. That means hot. This was where the black wire was. This one here, I labeled it ACN. That's for the neutral. The green ground wire was connected over here, and this is number 1. So that's one of the leads of the windings. And then on the other side, the other 3 leads of the windings will be connected to the other post on that side. Okay, we have the leads traced back on the other side of the switch. As you can see there, they're numbered 2, 3, and 4. And the corresponding lead numbers are marked on those leads. Now what I do in that situation is I just take a photograph of that, and I'll take a photograph of this, and it makes it that much easier to put everything back together. Now this is a simple project. I mean, I really don't need to number those, but it's just a habit of doing it. And if you're new at restoring any kind of a motor or anything, I recommend that you do that so that you don't make any mistakes. So I gave that shaft a light going over with some emery cloth because there's some burrs here from the set screws over the years. So now that's pretty smooth. Also, I want to mention that these end bells are mounted on the motor upside down. Normally the vent is on the bottom, but the reason why they're mounted upside down is because when this motor is placed on its side, those vents will be pointing away from the lathe and decrease the chances you'll get any metal chips in there. So that's the reason behind that. Now we're removing the 4 connecting rods that hold the end bells in place. If you hear any noise out there, I got a thunderstorm happening outside, so sorry about that. It's a good practice anytime that you're taking apart an electric motor to put a set of witness marks on the end bells and on the housing so that when you put it back together, you could line it up in exactly the same position it was when you took it apart. That'll help to prevent any binding in there. You can see on this motor the housing has a space here and here. That's for you to tap the end bells off. Now we're going to remove the front end bell first because that doesn't have anything attached to it. Back end bell is going to have wires attached to it and that centrifugal switch. So I'm just using a brass drift on this thing. You can see I already got some movement out of it. Okay, good. So the very first thing you want to do when you take an end bell off an electric motor is to observe whether or not there's any spacing washers in here. They're usually made out of a fiber material. Those control the play back and forth of the shaft, and they're real important because if it's not spaced correctly, it will bind up. So you can see where I got the tweezer there, there's one in there. So we're going to carefully remove that. We're going to make a notation of it and make sure we put it back in the same orientation when we put it back together. Okay, so now I removed the shield on the front of the housing. The proper way to do it is to use a slide hammer, but if you don't have one of those, you can take it out with a screwdriver, but it's going to get bent and you're going to have to straighten it out before you put it back in there. We're going to remove this little oiler here. That's a Gitz oiler. It just twists out. And on the back side, there's another shield. We're going to remove this one. I've already done it the same way. Okay, so this shield covers the packing material for the oil around the bearing. All right, so you can see there's a piece in there. Take that out of there. And all that wool packing material is going to be replaced. So we're just going to pull that out and throw it in the trash bin. So when you take out the small oiler here, it looks like this. You got the oiler, there's a little shield, and then underneath that shield is a little spring which kind of keeps the wool pressed down in there. Here's the wool that we've taken out. That's just going to get replaced, and we'll replace it with 100% organic wool yarn. Anyways, there's quite a bit of wool in there. It may not seem like it when you look at the motor from the outside, but once you pull it out, you'll be surprised how much is in there. Last step for this front end bell is just finishing to press out that sleeve bearing. Just using the arbor press for that. Boom. Just like that. So the front end bell is broken down as far as it can go. So now I'm going to just put it in a bath of purple power. That will accomplish a couple things. Number one, it will degrease it. And number two, if I leave it in there for a while, it'll remove all the paint off of there. Anytime you're dealing with these old motors or machines, you just automatically assume that it's lead paint. So you don't want to start using a wire wheel on it and create all kinds of dust. It's better to use a chemical stripper or something like that because it doesn't generate the dust. So in our case, we're going to use the purple power for the two end bells, and then on the housing, I would just use a chemical paint stripper on that. The front end bell is soaking in the purple power. Now we're going to go ahead and remove the rotor. I've already taken that spacing washer off of there. That hopefully is just going to pull us straight out. So this is the centrifugal switch we were talking about earlier that opens up to cut off the start winding from the circuit. Once again, we got some of those spacing washers, so the first thing I'm going to do is get a count of those and make sure we know where they go when we put the motor back together. The centrifugal switch is just held in place with a couple of screws, so I'll take those out and remove the centrifugal switch. So now we're going to remove the rear end bell. This one's going to have a bunch of wires attached to it, so we want to remove that carefully. Just going to lay it down. See how those wires that are connected? Now what we'll do is these screws right here, once we remove those, that terminal block with the wires that connect to the drum switch, we'll be able to remove all that and free up that rear end bell from the stator. Alright, so I removed the 4 screws holding the centrifugal switch in place. I cut the wires, and then I just renumbered those leads to the corresponding terminals on the switch. And we're going to carry on disassembling the end bell in the exact same fashion that I disassembled the first one, so I won't show that. It'll be the same process. Okay, so when I went to sleep last night, I put a little chemical paint stripper on the stator and wrapped it up in a plastic bag and got that paint off. I always just assume that these old paints have lead in them. I don't even bother to test them. I just assume that they have it and try to generate as little dust as possible. Anyways, as we carry on with this project, the next step is going to be to clean this stator up. And if you look here, there is a ton of heavy grease built up there on those windings. And that really has a detrimental effect on the windings because they can't breathe properly, and that can cause a problem with overheating. So since there's so much on there, it's caked up pretty heavy, and that's probably like grease and oil. I'm going to take this outside and I'm going to give it a gentle sprinkling with the hose and just knock off the big stuff. When I say gentle, I mean gentle. I'm not going to put the nozzle on a jet stream. Just going to gently hose it off and knock off whatever will come off, and then I'll come back and we'll do the rest by hand. Now, anytime that you rinse off a stator with water, you're going to have to go through a lengthier drying process to get these windings completely dried out before we revarnish them. So once you put water on it, you're in for a longer project, so be aware of that. At the same time, while I'm rinsing off the stator, I'm just going to rinse off the heavy crud that's on this rotor, and I'll bring you guys back as soon as I get that done. The rest of the cleaning will be done by hand. So the garden hose did a good job knocking off some of the heavy dirt and grease that was on there, but these are still real oily and greasy. Look at that, my finger. So in this cup right here, I have a solution of Dawn dish soap and water. I put quite a bit of soap in there. I want it to be a nice strong solution. Everything from this point forward will just be done with a soft bristle paintbrush. So you have to be real careful when you're cleaning these windings, and you don't want to be spraying brake cleaner or any other kind of cleaner on there unless you know the composition of this varnish. A lot of these older varnishes, you know, they were pretty fragile, so your best approach is a conservative approach. So we're going to use the Dawn dish soap and water, and any other cleaning that has to be done. The only product that I could recommend that doesn't do any damage to the windings is QD electronic cleaner by CRC. I use this stuff for all kinds of uses in the shop. I mean, it's just a great product when you need something clean and dry quickly. This stuff dries almost instantly, doesn't do any damage, but that is the only cleaner that you should ever use on your windings, in my opinion. So I'm going to get busy with this paintbrush and the Dawn dish soap and clean these windings up a little more thoroughly. Okay, everything is nice and clean now. I did hit a couple areas with the CRC just where there was some deep embedded grease. The other thing that the CRC does is it helps to push the water out of the windings, and then it dries real fast. So now what we're going to do is we're going to set the motor up with the heating pad inside of it and begin the process of drying out these windings so that we can work on it further. Okay, we got the stator wrapped up in the heating pad and a blanket over it to hold the heat in. We're just gonna leave that baking there all day long, just to dry everything out. This is a more conservative approach than putting it in the oven or something like that. You could do that if you were sure that you had an oven that could get down to a low enough temperature not to do any damage. But with this approach with the heating pad, it's impossible to do any damage to the windings with that because it doesn't get hot enough. It just takes a little bit longer. So while this is cooking, we'll work on other parts of the project. So I got the rotor in the wood lathe, and I'm just using that to polish it up a little bit. Obviously, if you don't have a wood lathe, you can do it all by hand. This just makes the process a little bit faster. So all I'm doing there is just cleaning up the surfaces a little bit, nothing major. Pulled the rotor out of the lathe, got that cleaned up. Just put that on the side while we continue working on the other pieces. So the next thing we're going to do is clean up the centrifugal switch. The switch consists of two parts. You have the mechanical flyweight mechanism here, and then you have the electrical contacts here. So we're just going to take our time, get in there with a small brush, clean those up. These contacts will get everything polished. You want to make sure that you have good electrical connections there, so everything should be nice and shiny. Alright, here's how it looks when it's done. It's kind of hard to film that when I'm putting it back together because I'm trying to concentrate on that and the camera at the same time. So that's how it looks right there. When you press on this, see how those open up like that? And that's what's going to activate this contact. Okay? I'm going to call that good. In between other parts of the project, I'm just giving the hardware a light polishing. I'm not spending a lot of time showing that because I don't want the video to be too long. We'll just stick with the important aspects of the electric motor restoration. Okay, so now we're going to do what's called a Megger test on the windings. And the purpose of the Megger test is to determine how good the insulation is on the windings. So what this does is, this little device right here, you crank it by hand. They also have digital ones if you'd be interested in getting one. Anyways, you crank it by hand and it puts a voltage through the windings. So you can see here, one lead is connected to the winding and one lead is connected to the housing. And it measures the resistance of the current from the windings to the housing. So anyways, in an ideal situation, you want this meter to read what's called infinity, which means, you know, it's excellent insulation. Having grease and dirt and moisture, all those things will really have a huge impact on the insulation resistance. So this is the first time I'm even taking this reading because I didn't want to do it until I cleaned all that oil and grease off the windings and hosed them off and got everything nice and clean. And then if you'll recall, I put the heating pad on there and let them dry out thoroughly. So it's pointless to take the Megger reading while the windings are dirty because it's going to be low. Now that they're cleaned up a little bit, we're going to take the reading, see where it's at, and then we're going to start reworking these leads on here, and we're also going to recoat these windings with a brand new coat of varnish, and then we'll warm them up again to make sure that that varnish cures nice and dry. So I'm going to step over here and I'm going to start cranking this handle. Now the way that you're viewing the Megger on the camera, we want to see that needle go to the right. It's probably hard for you to pick up all the numbers on the meter, but you want to see the meter going to your right, which is where the infinity is at. So when I start cranking this, okay, you can see that we're maxed out. Okay, that's exactly what we want to see right there. So now I'm going to move it over to the next winding, because don't forget you got a couple sets in there. We're going to crank it again. Okay, we're maxed out again at infinity. So these windings are in excellent condition. Now we're going to start soldering some new leads on there. The first step in redoing the leads is to put a piece of heat shrink tubing. As you can see here, when I cut these, I didn't cut them all the way back. You don't want to do that in case you need to work on them in the future. You want to leave a little meat on the bone, so to speak. So anyways, in this area, you can see where I put a little bit of heat shrink tubing. I'm going to do that for the 4 leads, and then we'll solder on the new leads from these ends. See what that sign says right there? In this box here, I got rolls and rolls of original cloth-covered wiring. So I do a lot of tinkering around with motors, and a lot of times I like to use the original cloth-covered wiring if that's what was on there. So when we resolder up these leads, I'm going to pull out some black cloth covered wire, and that'll be very similar to what was on there originally. Alright, so I was just going through my brass hardware because I wanted to add 2 more binding posts to this terminal block. Originally when we took it apart there was just the 2 here, but there's 4 leads that come out of there. So when we put it back together, we're going to have each lead attached to its own binding post, and in the future if we ever need to change that cord again, it'll be easier to do it. Now we're going to begin re-insulating the windings. I'm using this product Spray-On EL600. It's a clear insulating varnish. It's made specifically for electric motors. It's a great product and it's easy to apply in an aerosol can. We got a nice liberal coating of the EL600 on the windings. This varnish will air dry, but I like to put the heating pad on there just to help it cure a little bit better. So I'll get that set up and the windings should be good to go. So the bearings I had on hand didn't have a hole in there for the oil wick to go through. And when you're drilling into bronze bearings like that, they tend to catch the drill bit. So that's where these things come in handy, these hyper step drill bits. I'm not exaggerating when I tell you that these drill bits are the best drill bits I ever used in my entire life. Now I'm just using the die grinder to enlarge those holes a little bit. Making up some new oil wicks out of some organic wool yarn, and I'll saturate these with oil before I pack them in there. Okay, so it's not unusual when you press in new bearings that you have to fine-tune them a little bit to get them to fit on the shaft, because the shaft is 5/8 of an inch in diameter. I just mic'd it and it's almost exactly 625 thousandths. The thing is, the bore of the bearing is also 5/8 of an inch, exactly. So 2 objects of the same size can't occupy the same space. And so once you press that in, okay, it compresses a little bit more also. So I just used a little bore mic on there, and it is indeed a little bit smaller than the shaft. So we're going to use what's called an adjustable reamer, and we're just going to enlarge that hole a little bit. So I have that adjustable reamer set now where it just fits inside the bearing as is. So now what I'll do is I'll pull it out, I'll just take it up just a few thou, I'll ream it, and then test fit it, and then repeat if necessary. So working with these adjustable reamers, you just want to take your time, move slowly, then like I said, when I'm done with it, I'll make sure it's perfectly clean before I put it away for the next time. Now that I'm done with the adjustable reamer, I took it completely apart, got it perfectly clean, so when I put it away, it'll be ready for next time. If you treat these things like you would a micrometer or other precision instruments, they work a lot better than you'd think. Okay, I just screwed in the switch onto the rotor. That was held in place with the 2 screws. And over here, I screwed in the electrical part of the switch in with the 4 screws. Now I'm just going to go ahead and resolder those leads back onto the terminal block. Get this thing put back together. So I'm doing a test fit of the motor, and I would like the shaft to turn just a hair easier than what it's turning. I mean, you can see it's turning, but it should be turning just a little more free than that. And what causes that is when you put new bearings in, the bearings are not exactly aligned with each other. So that's where these come in, okay? This is a set of extra long aligning reamers, and what they do is they'll actually true the bearings up to each other. So what I'll do is I'm just going to take the rotor back out of there. I'll set the alignment reamer at the size of one of the bores and then just flip-flop it end for end, and that'll just true them up with each other, and then that thing will be spinning just fine. All right, so we took the motor back apart real quick, and I I was ready to go to town here with my aligning reamers and get that fine-tuned. As I suspected, you know, there was just a little bit of an alignment issue when I put it back together. But the actual problem wasn't the bearings. What I realized once I took this thing apart is I inadvertently left one small strip of painter's tape on there. I didn't take that off when I put it back together. And the thickness of a little piece of tape like that might not seem like a lot, but in the world of bearing tolerances, that's more than enough to push those bearings out of whack. So I'm going to clean that, pull this off and clean that area up, and then put it back together, and that'll probably fix the problem right there. Since I already had the alignment reamers already out, I went and I set the alignment reamer for 2 thousandths over our nominal size, which these shafts are 625. They're pretty much right on the money. Okay, I put the end bells in the motor without the rotor in there, and using this, okay, this aligns the reamer with the other bearing, gets them trued up. So I just took what would be considered a skim cut, and if you look, I took off just a tiny bit of material in there and just trued them up with each other. I mean, since I already had it out, I said, well, let me double check it. And then I went ahead and I put the rotor back in there. As you can see here, okay, that thing spins beautifully. And we have just the right amount of axial play in there. If I put one more washer in there, it would be too tight. So you need a little bit, and the rotor will find its electronic center once it starts moving. So in order to test this motor, because we don't have the drum switch restored yet, I put 2 little jumpers in there. Okay, you have to connect the run winding and the start winding, so I had to jump those little terminals together in order to be able to test it. And I have the motor hooked up to what's called a variac, and the variac will allow us to bring the voltage up slowly to the motor in case there is any problems. The variac will allow us to test the motor in a controlled fashion. So we're going to turn the variac on, and now when I move this, okay, we'll bring the voltage up slowly, and hopefully we're going to see some movement here, which we do. Okay, you just heard the switch kick out. This motor is rated to run on 115 volts, and there it is at 115, and I'm going to bring it up to our line voltage, which is 120. Okay, as you can hear, that thing runs whisper quiet. That is perfect right there. If you recall, in the first part of the video when I tested this motor, there was some rubbing because those bad bearings were in there. So now this thing is really running nice and quiet. So now that we have that done, we're going to go ahead and restore that drum switch, and I'll get the rest of this motor buttoned up. Carry on. So in order to get these last 2 rails out of here in this piece of insulation, you have to gently bend back those tabs. Okay, so here's our drum switch completely broken down. Once you take this thing completely apart, it actually has more pieces than you would anticipate. So we're going to get this all cleaned up, repainted, put back together. Alright, this is our finished motor. Really came out looking beautiful. It's probably better than when it left the factory. Anyways, when I put the motor back together, I put it back together in the same orientation which I took it apart. Matter of fact, you can see those little witness marks up there that I marked it, so I put it back together the same way. In my mind, those end bows should probably be turned around the other direction for chip control, just making sure that nothing could fly in there. I'll monitor it and see how it is. The motor does exhaust air when it runs with that fan in there. And these will be sideways. I mean, it shouldn't be too much of an issue, but to me, it seems like they should be turned around. So I'll give it a try, and if I need to rotate them, it's not really a big deal. All right, so my OCD would not allow me to put that motor back on there with those vents facing in the wrong direction, even though that's the way they were before. So I flipped those vents around 90 degrees, and in order to do that, I actually had to shorten the leads in there a little bit to accommodate that, but no problem. It's all done now. Motor's ready to be installed. All right, we got a terminal soldered on there, and we put some heat shrink tubing around each one of them, so that's a nice solid connection. And out of our junction here, I'm using some stainless steel flexible conduit to run the cables to the drum switch, so that's going to work out real nice. Here's the drum switch mounted. There's the cable running around the side. Got the motor on there. Got a brand new belt here. I did end up putting a 45-inch belt on here just to give me a slight bit of clearance between the motor and the machine. Before it was only like 1/8 of an inch, and with this belt it gave me a little bit more clearance. Because of that, I remade this piece here, and that's working like a charm. So now what I'm doing is, I noticed that when I snugged up these bolts that hold the bearing assembly for the headstock wasn't moving as freely as it should. So it was almost too snug. I was checking it with the dial indicator, and once I snugged these down, there was almost no give in there at all. And there has to be, according to the South Bend manual, keep your lathe in trim, there's supposed to be about 2/1000 clearance in there to allow oil to circulate. So I got some brass shims that are 2/1000 of an inch thick. I'm going to go ahead and put a shim on each side and try it like that, and I'll adjust it as necessary. The 2/1000 brass shims that I put underneath these headstock bearings seems to have worked perfectly. I was able to get these bolts snugged, and we got like 1.5 thou movement out of that, which is right within spec actually. So another thing that I did was I drilled a hole here and I drilled a hole here so that I could get some oil on those back gears, because there was no easy way to oil them without taking those guards off. Now what I'm doing is I have my tailstock alignment tool here, and I was just adjusting the tailstock, making sure that that it's completely in line with the headstock. If you watch that mic there, okay, that thing is dead nuts on. So we're getting close to making our first cut. Just buttoning up a couple loose ends and we'll be ready to roll. So here's the machine when it's running. And as you can tell, it runs really quiet. You don't hear any rattling, the gear train is quiet. So that's about as good as you could ask for an old South Bend lathe. So I'm still making some fine-tune adjustments on this thing. I was playing around with the tension of the gibs. I need to loosen them just a hair. They're just a hair snug. Before they were too loose, I tightened them up, now they're a hair tight. I was playing around with the saddle lock and making sure that nothing moves, you know, when we're making a cut. I chucked up a piece of 12L14, commonly called lead loy. This is some pretty easily machining material, which is what I want to use, you know, when we're just making adjustments here. I'm running the machine slow, feed rate is slow, shallow depth of cut, you know, we're just kind of feeling the machine out and making adjustments as necessary. We're not really worried about the surface finish or anything like that. I did buy a bunch of high-speed steel, which I'll need to grind up into some tool bits. So that'll be a job in itself. I really need to practice that. I'm no expert on grinding high-speed steel, but I'm looking forward to learning it. In the meantime, I just got a little piece of carbide in here. For what we're doing here, it'll be fine. So I already touched off on the piece, and I got a center in there. And let me fire it up and check it out. there's the finished cut. Came out looking pretty good. I mean, it wasn't real deep, but you get the idea. This tooling that we got in there right now is only 1/4 of an inch, so it deflects a little bit. I have a quick change tool post, and I have some 3/8 inch tooling that I'm going to be putting on here, but I need to machine the nut to fit on there. And once we do that, the whole setup will be a little bit more rigid. So I'm going to keep playing around with it, you know, work the kinks out of it, make adjustments as necessary. Just taking conservative cuts right now, just feeling the machine out, nothing major. So I hope that you've enjoyed following along the process on both the restoration and the rebuild of the motor on this lathe. It was really a fun job, and I'm looking forward to learning more about machining. And I think this is a great lathe to embark on that path. So I appreciate you watching the video. We look forward to seeing you folks the next time. Take care.